CV, control volume. Is it a local approach or a global approach? Global approach. What do you do with this formulation? Approximate velocities and find forces. In the local approach, you express forces in terms of velocity and pressure and find velocity. So, in the local approach, you are finding velocity. In the global approach, you are finding the force. That requires evaluation of integrals. That evaluation is through an approximation, not analytical evaluation of the integral. In this book, they show 3 integrals for volume and 2 integrals for surface. So, I have not shown those many. If I say d integral dv is of course a triple integral, doesn't matter because you are approximating it as average value of the integrand over the volume times volume. So, let us say we are addressing incompressible flow problems, then mass balance is given by this equation. Let us say steady incompressible. So, these are the equations to be evaluated. So, in the simple example we looked at, which is flow through a tube, the integrals are evaluated by splitting them over the inflow plane, outflow plane and the wall of the tube. So, when you split, then you are in a position to evaluate the averages, average value of the integrand much better. So, we got this result. So, let us say for flow in a tube of variable cross sectional area, so you pick up so that 3, the lower side is also 3, it is the same 3 all around, and u dot n is 0 on that surface. So, we got this result that the x component force is equal to m dot u2 minus u1. So, if it is flow through a tube, then U1 is equal to U2, and the force acting on the tube, well, let me be a little more specific. Force acting on the control volume that we have picked up for the tube, for analyzing flow through a tube, that force acting on the control volume. Control volume contains the fluid medium. Control volume is fixed, there is a tube and flow is going through. The force acting on the control volume is 0. That is what we get by approximating the integrals. Can interpret this result a little more by looking closely at the force field. So, recall our notation for force distribution acting on a fluid element in terms of stresses. So, where are these forces acting? These forces are broadly classified into surface forces and body forces. Body force is in a gravitational field, it is the weight of the fluid medium, and it acts in the vertically downward direction. So, here for analysis we have taken a horizontal tube, we were doing calculations in the horizontal direction. So, the vertical force that is weight does not come into reckoning. So, let us keep, but it will come into picture in other calculations as we will see later, not in this particular calculation. How do you handle weight? That also we will see. There is a shortcut for handling weight by dealing with pressure. You remember our discussion that weight will impact pressure distribution in a hydrostatic context. Now, here there is no flow in the vertical direction, so it is hydrostatic in that direction. So, we will discuss that point a little later. For the time being, in the x direction, body forces arising from gravity do not come into picture, and then you have surface forces all around. So, the moment you pick a control volume, you will have a distribution of forces acting on the control surface, whose resultant is this F. Okay, so, resultant of body forces and surface, all of them together is this F. So, if you can do some hair splitting, so to say, go and see what is happening closer to the force distribution. Now, when you talk of force distribution, it is on a per unit area basis that gives us the stress notation. So, I am going to call this the stress notation. So, similar stresses act on all faces of this element. Now, we are interested only in the x component. So, those would be, let us call this the stress notation. And if you look at only those stress components that contribute to forces in the x direction, okay, so sigma yx, which is a shear stress acting on the top surface parallel to it. Sigma xx is a normal stress component acting on the surface on this vertical face. Okay. Similarly, of course, you will have horizontal components on other faces. Now, I just mentioned that a very dominant component of the horizontal stress would be pressure with a negative sign. This is in the right handed coordinate system, but pressure is taken to act in a, it is positive in compression. So, sigma xx will be minus P under hydrostatic conditions, but under flow conditions it will be minus P plus some correction term, but there is no way flow in the vertical direction. So, it is practically equal to minus P. Okay, so, now this is the control volume. So, on the left plane you have pressure P 1 and on the right plane you have pressure P 2, corrected of course for hydrostatic effects, which for the time being we can neglect on various grounds. One of them is that you need something like 100-meter variation in water depth if it is flow of water. In terms for gases, it could be kilometers before you see the effect of hydrostatics on the pressure distribution. Now, this tube is a small tube. So, we assume P 1, P 2 to be constant in the vertical direction, but there is a variation from P 1 to P 2. So, these arise from this sigma x x, okay, applied to this control volume. Then on the sides we have picked the side boundary to overlap the tube. So, on which u dot n is 0. So, and the flow, the tube is like this, flow is that way. So, there is a shear stress acting on the surface, equal opposite will act on the tube. So, using this notation you can write it as, and the lower surface is the same surface. So, I do not have to show it on the lower side, it is the same surface sigma y x. Now, what is the symbol that we use for sigma y x evaluated at the solid fluid interface? The symbol used is tau w, right. Tau wall is same as sigma y x evaluated at the wall. So, this is equal to tau wall. Okay. If you are in the interior of the fluid, you still have a sigma y x. Any time you extract a small portion of the fluid and show it separately, there is a force field acting on it, and you write surface forces plus body forces. Okay, so, f x, which is 0, can be written as P 1 minus P 2 times the cross sectional area plus tau wall into some 2 pi r L. So, looking at the distribution of forces. So, we have gone a step forward, because pressure P arises from, as we had discussed, from particle level motion of the fluid. It is thought of as a thermodynamic quantity, while wall shear stress is completely a flow quantity. If there is no flow, there is no tau wall. So, this expression is slightly useful because it relates wall shear stress to changes in pressure. So, this capital R is the radius of the tube and L is the length of the, or the distance between 1 and 2, okay. Plane 1 and plane 2, that is L. So, does it have any, A is cross sectional area, is there any other information? Well, not really, just if you stick to the equation, there is nothing else you can see further. But if you take recourse to Newton's parallel plate experiment, which tells you if you move the plate, the fluid is dragged with it, and a velocity distribution is set up in the gap. So, conversely, if there is flow taking place in a tube and the fluid particle comes to rest at the wall of the tube, that was the no slip condition we discussed last time, then there has to be a force acting on the CV in the opposite direction. So, if you reason it out that way, though of course, See, if you go to a local approach, all these details will come out automatically. The global approach, you can go some distance, after which you have to infer. In the local approach, the complete solution including the sign will get revealed. So, that way local is a lot more powerful. This is your first course on the subject. So, we start with a simpler step, get some quick answers. So, if the fluid is going to be held back by the tube, what can you say about tau wall? It has to be in the opposite direction, that means opposite to the sign that is shown. So, if tau wall, suppose your reasoning tells you that tau wall is really negative. Why do we write it? Inspired by Newton's parallel plate experiment. Then, if this is negative, that means P 1 minus P 2 is positive, that means okay, so P 1 is greater than P 2. So, that means when you have flow through a tube, pressure progressively decreases in the flow direction. At some point, there is an exit of that flow that will be under atmospheric conditions, which means that on the left plane, this being the left, pressure has to be higher. So, that means you need a high pressure reservoir on this side to sustain flow. So, to create flow in a tube, you have to create pressure difference. Let us say one side is atmospheric, the other side is a high pressure reservoir, or a device such as what? A pump for liquids, compressors for gases. That is the terminology often used. The pump is used for liquids and compressors for gases, which generates that high pressure on one side. Then you connect a tube and there will be flow. So, this is how we carry out analysis. That means, you have some preliminary results and then you infer what could be happening in the flow field by examining the force per unit area distribution over the control volume. Okay. So, let us continue this trend of thinking and apply it. That was this flow through a tube is an internal flow problem. Flow is confined. Now, let us look at an external flow problem. The flow is happening and you place an object in it. So, what could be this object? Any object going from an aircraft all the way to a chimney, or it could be you riding a bicycle, not a motorcycle. Our analysis, does it hold for motorcycles? Yes, but I do not like it. So, you will not see that example, but bicycle example you will see. Okay. So, you are riding and then you are experiencing some force, and I will tell you, approximate yourself as a flat plate. Okay. So, then you go from a particle to a flat plate. Okay. So, God forbid you become a cylinder. So, the model for external flow, it's a baseline example. So, this is CV . CS . It is U equal to capital U everywhere. Just so, this represents not just gentle flow, just a uniform flow. Gentle breeze or a strong breeze, you might have experienced it if you go beyond some 7th floor or 8th floor of a building, there is always a constant breeze. Okay. So, for tall buildings, gentle breeze is reality, and that gentle breeze can become intense on certain occasions, can become a storm. But the power of Newtonian mechanics is it carries over, whether it is bacteria in water all the way to cyclone or storm impacting a building. That is one. The other is, I keep saying, aircraft. So, in the aircraft setting, the object is moving at, let us say, constant velocity. When it is moving at constant speed, it is equivalent to gentle breeze going past that object. Okay. So, both are covered. So, here of course, if it is water, there would be a hydrostatic pressure variation. If it is air, then pressure is practically constant. So, in the hydrostatic context, the pressure variation is in the vertical direction, but if you look at forces in the x direction, which is the flow direction, then hydrostatics will not play a role. So, if u is equal to capital U everywhere in this baseline flow field, then there is a shear stress distribution all around. How much will that be? Shear stress depends on change in velocity, like in the Newton's parallel plate experiment, right? One surface fixed, another surface at some velocity capital U, and we said stresses depend on the difference in velocity between the two surfaces, namely the gradient in velocity at any point. So, shear stresses are all 0 in this baseline example. Sigma I j equal to 0 for I not equal to j, and sigma I j equal to minus p for I equal to j. Okay. So, shear stresses are 0. If you put shear stresses equal to 0 in the tube problem, you will get P 1 equal to P 2, is it not? Because for this problem also you apply momentum equation. I think sometimes in the book they call it momentum theorem. So, it is just Newton's second law of motion. So, it is momentum equation, and u is equal to capital U everywhere will give you the y component of velocity equal to 0 everywhere, right. This is v equal to 0. So, this flow, uniform flow coming in, and there is no transverse velocity. So, f x equal to 0 on one hand will give you p 1 equal to p 2. So, this sigma I j, that is the stress distribution, is constant all around. Okay. So, now in this field, this is our baseline flow. In this field, we introduce an object. Okay. Could be a cylinder, sphere, aircraft, human being, automobile, whatever it is. We insert an object which disturbs the flow field. So, then u equal to capital U, v equal to 0 is only the inlet condition, elsewhere flow has to go around the object. So, now we look at this configuration, flow over an object. Okay. So, and apply the mass and momentum equations. Okay, so, integral C s equal to 0 and f x is equal to rho integral C s this is the original form, and this u will be equal to this vector u should be replaced by the x component. Why? Because you are working with the x component force. Okay. So, though I have shown u tilde, it really is the x component that you should use in the momentum equation. So, how do you pick your control volume? Control volume should contain only the fluid medium. So, now the control volume is split in two parts. One is the outer boundary and second is the inner boundary. So, you exclude the object. So, you may call it CS1, CS2. CS2 is the object, and then CS1 has four parts: left plane, right plane, top and bottom. It is not okay. This is no longer a tube kind of a geometry. We are talking about a planar geometry. So, we can identify four planes in CS1. Okay, so, A, B, C, D, 1, 2, 3, 4 and 5. These are the portions of the control surface. So, there is integral over C s is written as integral over 1 plus integral over 2 plus integral over 3 plus integral over 4 plus integral over 5. Okay. Now, it is a solid object. So, u dot n on that surface is 0. So, proceeding to mass balance, so this is u1, u2. So, u dot n for 5 is 0. So, for the left plane, the unit normal is on the left. So, it gives you minus u1 a1. So, this is the unit normal here. Here, this is the unit normal. Here, this is the unit normal. So, u and v are the x and y components. So, let me also stipulate that it is external flow in a plane. Okay. So, if you place an object, I think you can almost imagine that if you block the flow, then flow will go around the object. So, there could be some flow taking place vertically upwards on the surface 4 and below on surface 3. So, the y component of velocity will get activated. So, let us call this V3, this is V4. Okay. So, V3 and V4, what are they? They are the average value of the y component of velocity on planes 3 and 4. Why average? Because only then you can evaluate the integrals. Okay. Really speaking, there is a distribution, everything is distributed in space. We are talking about steady flow. So, there is no time per se in this discussion. So, u1 is in this direction, u2 is also that way. So, minus u1 a1 plus u2 a2 plus V3 plus V4 times let us say this width, I will call this W equal to 0. Okay. This is the mass balance equation. Now, moving on to the momentum equation, you will have F equal to rho times, again the integral is split into so many parts. U dot n on the object is 0 again. So, you are left with 4 integrals. On the left plane, this left plane, u is equal to u 1. On the right plane, it is u 2, but u dot n will be minus u 1. Okay. So, you have to factor in that sign. On C D, what is this x component of u? It is it's the x component of velocity prevailing on C D. So, now let us start with a new slide. So, just for the sake of analysis, you remember that in flow through a tube, you picked the side boundary to overlap the tube to simplify analysis. Okay. Now, in this problem also you can pick your side wall so that it simplifies analysis. In general, you do not know the x component of velocity on the side wall, but if you pick it slightly far away from the object, that means control volume is reasonably large compared to the object. If you do that, then that is undisturbed flow. What is undisturbed flow? Which is the inflow. So, here you make a choice with a view to simplify the integrals. This is the object. So, I am talking about this side plane as well as the side plane below. In the jargon of fluid flow, the term used is it is far field. If you are close to the object, it is called near field. If you are away from the object, it is called far field. Pick the side boundary to be far away, so that the x component of velocity does not show any influence of the disturbance created by the object, and in that case it will be equal to the inflow. So, x component of velocity on surface 3, that was surface 3 I think, u 3 as well as u 4 can be written as u 1. Okay. So, with this you will have rho times minus u 1 square a 1 plus u 2 square a 2 plus V 3 plus V 4 times W all multiplied by u 1. Okay. But if you look at the expression for V 3 plus V 4 times W is u 2 a 2 minus u 1 a 1. Or was it with the other way around? Negative of this, yeah. It should be u 1 a 1 minus, yeah. Like this way. Okay, which is inflow minus outflow is the flow going out on the sides. Okay, because you have now blocked the incoming flow. If you do not block it, then of course, whatever comes in goes out. So, now you just substitute and see, you can see u 1 square cancels off. So, this is just rho u 2 a 2 multiplied by u 2 minus u 1. Okay. Of course, rho U2A2 has units of mass flow rate, but it is not the mass flow rate. Mass flow rate changes from point to point because there is some flow through the sides. Okay. So, you can define an incoming mass flow rate, that would be rho U1A1, okay, but that is not equal to rho U2A2. The difference between them goes out from the sides. Sides are open. There are no solid walls here except the solid object. So, that is why it is called an external flow problem as opposed to internal flow. So, you now if you look at this result a little more closely, how can you interpret it? If you block the flow, so let us say this is U1, and then what do you know about U2? If you block the flow and some flow is going out from the sides, then U2 will, really speaking, if you look at the distribution, it will show a kind of a dip along the axis. And far away we said the far field is chosen to be undisturbed. So, you can expect U2 distribution to be something like this. This is U2. So, far away U2 becomes equal to U1, but closer to the, let us say, mid plane, it is smaller. Okay. So, under these conditions, you can conclude that U2, with this U2 here in the expression is the average value of the distribution, right, and that average value is smaller than U1. So, U2 is less than U1, therefore, f x is negative. That is one conclusion. So, this is what is f x? It is the force acting on the control volume. So, the force, okay, so let us write down on control volume. Now, this is a further, let us say, a closer analysis of the force field. This force field is not localized, it is a resultant, but it is not localized. It is, where does it appear? It appears along the control surface. How many control surfaces do you have? 1, 2, 3, 4 and 5. And now you are talking about the x component of the force. Okay. Now, we have already said that the control volume is quite large compared to the object, so that the far field is undisturbed. So, on plane 1, so I am now going to show the force distribution on the control surface. So, you have P 1, P 2, only x direction. Of course, you have P 3, P 4 also on the sides, but they are in the vertical direction. And then the shear stresses, there is a shear stress on the inlet plane also, but that is in the vertical direction. So, here let us show the shear stresses. There are shear stresses acting on the side planes, but in the far field velocity is uniform, therefore, the shear stresses are 0. So, the far field is uniform, the control volume is chosen to be large compared to the object. Now, how large is always an open question. Okay. So, it is like asking, suppose I approximate the integral as average value of the integrand times the volume or area. The question is how approximate is that answer? That depends on the manner in which the average is computed. Okay. So, shear stresses, see on this horizontal plane on surface 3, it is sigma y x shear stress, and it is not tau, because tau is a symbol we use for a solid surface. P 1 is equal to P 2. Then there is also a stress distribution acting on the object all around. In the far field, the forces add up to 0. Okay. That means, the resultant force we have calculated is localized on the object. It is acting, and even though u dot n is 0, all the force that we have calculated is localized on the object, because the far field does not contribute to this resultant. So, this Fx, this was on the control volume. So, now on the object, Fx is equal to rho u2 a2 u1 minus u2. So, now u1 is greater than u2. So, this is positive. That means, a force, an object, you have flow, you place an object, it is going to experience force in the same direction as flow. Flow is in the positive direction, force also is in the positive direction as far as x components are concerned. Okay. So, normally again every subject is full of jargon, and this jargon is so commonplace. You see it even in informal settings. Any idea what this force is called? Force acting on an object in the flow direction is called drag, and force acting on an object in a direction normal to the flow is lift. Okay. Lift and drag. So, last time we also said some forces are parasitic, useless, and some are very useful. So, you know intuitively that drag. For example, you are riding and the force that you have to overcome is, on one hand you can think of as parasitic, on the other hand if you see it as exercise, it is really good. In the aerodynamic context, you want that lift to support that aircraft mid-air. So, it is very useful. Let us take a look at one more example. Let us see. Yeah. So, these are typical examples we consider in fluid flow, because they do have plenty of applications. Incidentally, are there any constraints on the shape of the object? Essentially, it can be any shape. It can be the wing of an aircraft or an aircraft. It could be stone, it could be, like we said, it could be a chimney. So, in that case it will be the cross section of the chimney. So, that makes the method very general, it is not geometry specific, because there is no evaluation taking place on the surface of the object, everything is in the far field. So, also note that we have estimated forces from an approximation of the velocities. So, these geometries are sort of regularly studied: flow through a tube, flow over a flat plate, this flow over a circular cylinder. These are some reference geometries that are widely studied, for which a large amount of experimental data is available. Now, speaking of experiments, you can always ask, we have approximated the integrals, we should have used u2 square average, that was written as u2 average squared. You understand the difference between the two, right? Two are not equal. So, how useful is this estimate? You have found the force acting on the object. Is it useful? That question can be answered only with reference to experiments. You carry out an experiment and measure the force, and then you also calculate force using this approach. Compare the two, and it turns out that these estimates are indeed close. Now, how close is close? Is 0.01%? No, more like 5%, 10%. Okay. So, these forces, where are they used? Subsequently, they are used in design, and the design engineer also knows these are all estimates. So, he or she will jack up the force for calculations. Suppose you have a chimney and you estimate force this way, you can always double it up and then put supports for it. Okay. So, there is an element called factor of safety, you might have heard of, which goes into the process of design, where estimates are amplified, exaggerated, and then used for finalizing the structure. But still, even without that exaggeration, the estimates are within 5% or 10%, not 0.01%. So, sometimes they say, students read articles in the newspaper saying, this person was able to measure the speed of light correct to maybe the 14th decimal place. So, those are required in a very different context. Here we are talking of, it is not, it could be 10 newtons or it could be 14 newtons, that kind of a range. So, let us study flow over a flat plate. And let us say the plate has 0 thickness. So, it does not block the flow, it is aligned with the flow. So, you set up a control volume. So, the plate is here. So, we are showing the control volume, but this lower side overlaps the plate. So, you have A, B, C, D. C, D is open. This is U equal to capital U, which is of course in our notation, it is also, this is inlet or inflow plane, this is outflow plane. On AB, U dot n is 0, and on CD it is an open boundary. So, in principle you can have, so this is let us say surface 3, there is a normal velocity v 3. So, this width is w and this height is h. C d is chosen to be the far field. Okay. So, applying now, let me rush through the steps because we have done the same thing earlier. So, you have minus u 1 a 1 plus u 2 a 2 plus v 3 times w equal to 0 as mass balance, and momentum, let us say f x is equal to rho. This control surface has 4 planes. On A B, u dot n is 0, so it does not come into picture. So, you have minus u 1 square a 1 plus u 2 square a 2 plus v 3 times w plus times the x component of velocity, which is u 1, because it is in the far field. And for v 3 w, you can write it as u 2 a 2 minus minus plus u 1 a 1. Okay. And this also will turn out to be like in the previous example. It will be rho u 2 a 2 multiplied by u 2 minus u 1. It is the same expression as before, which again, okay, now here you do not know if the object is blocking the flow, it is aligned with the flow, it is not the same thing as an object. So, will u 2 be less than u 1 or will it be greater than u 1? Immediately you do not know, but you can proceed for force calculation. So, like in the previous example, this force will also be localized at the wall. So, so, if you look at this surface and there is flow over it, so, what are the forces acting on that surface? They will be equal and opposite to the forces acting on the control volume, right. So, you have in the vertical direction you have a pressure distribution, and I mean it is in the it's sigma y x. Why do I show sigma y x that way? It is being consistent with the class. Okay. So, we will complete this problem. Flow over a flat plate will be our starting point on Monday. Oh,